Welcome to the second video in SLO8. In this video we'll be looking at representation systems for carbohydrate structures in more detail. So I've shown you two structures here, glucose and ribose, and to layer into our stereochemical discussion from the previous video, the letter D in front of the name of the sugar corresponds to which enantiomer of the sugar you're looking at. So L-glucose would be the enantiomer of this structure, where all the wedges and dashes would be switched, as well as D-ribose. And then we have our new representational form start on the bottom. So this is the a different representational form for D-glucose. So these two structures are the same structure represented in two different ways. And these two structures here are the same structures but represented in two different ways. So to get us started and to help review what you did in video 1, what I'd like for you to do first is to actually come up with a name using aldo and keto and carbon count prefixes to describe D-glucose as well as D-ribose. So go ahead and pause your video and come up with those names for these two structures now. Analyzing D-glucose, we can see that there are 6 different carbons. So this is some kind of a hexose, and then we have an aldehyde group present. So glucose must be an aldo hexose. Playing the same game, we're using the same rules. For ribose, we see that this has 5 carbons and is also an aldehyde, so this would be an aldo pentose. Those decisions are going to be important for us as we interpret this new kind of representational form that we're going to call a Fischer projection. So the name Fischer might sound familiar to you because it's the same person who developed the Fischer esterification. So this is work that, or the system of representation, so these structures here and here, or these drawings, was developed by a chemist named Emil Fischer. He's a German. He was a very famous chemist who, among other things, actually worked out all of the stereochemical relationships among all of the possible hexoses, which are kind of some of the more common biochemical sugars, so the ones we tend to find in organisms, for instance, which is an amazing feat. So this was done in 1887, which is long before the invention of any kind of experimental techniques like IR or NMR. So Fischer worked out structures like this for glucose, for instance, versus like mannose, a structure we saw in the previous video, purely by using melting point, which is kind of incredible. Fischer also had a lot of other important contributions, including things like the Fischer esterification, so he's one of the most famous and one of the most influential chemists in history. So what Fischer wanted to do was represent stereochemical information as well as the information encoded in these green names as quickly as possible. So he could draw structures as quickly as possible and communicate especially differences between structures. But we know how to interpret line angle drawings. We don't know how to interpret Fischer projections yet. So my goal is to have us actually look at Fischer projections for D-glucose as well as D-ribose to help come up with a system or a set of rules to interpret Fischer projections. So if we know that D-glucose is an aldohexose and D-ribose is an aldopentose, then we should be able to see the difference between hex and pent in these two structures. So what I'd like for you to do is try to figure out what in a Fischer projection is communicating the number of carbons that are present. And you can help figure this out by looking at the difference in structure here, which should have 6 carbons, and here, which should have 5 carbons. So pause your video, come up with a rule that correlates carbon count to some structural feature, some drawing feature in a Fischer projection. So one thing that we notice if we look at the Fischer projection of glucose is that there are a set of lines that cross in places, and that those crosses and lines are a little bit like in line angle drawings, where we have these kinks, and that those kinks or ends of lines end up corresponding to carbons. So one hypothesis that we can generate is that these crosses, so this cross here, 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 maybe those are carbons. I know that there's an OH group and an H group attached to a carbon, so OH and then an implied hydrogen, so that might work. But this only gives me 4 carbons. I notice also that there seems to be something that looks like an aldehyde, so this also looks like a carbon. And then finally, down here at the very end, this bend in the chain, this 90-degree angle, looks a little bit like a carbon that has maybe an OH group and nothing else attached, which would be like this carbon here. So what we can see, maybe, is that it's both the ends of this vertical line and also the crosses that correspond to carbons. That's like a hypothesis for a rule. So let's check it against the ribose Fischer projection. So here we see an aldehyde carbon, and then cross, across, across, and then a carbon at the bottom of this vertical line. So if I look at all of the places I think there might be carbons, I come up with 5, and it looks like our rule works. So for Fischer projections, we can say that carbon is equal to an intersection of lines or a terminus of the vertical line. Excellent. The other thing that we can see in a Fischer projection is that some functional groups are as we would represent them now. Alcohols, aldehydes, that kind of thing. So carbonyls, and OH groups represented as normal. And it looks to me like there's one other thing that we want to note, and that's that at least with respect to some of these carbons, the hydrogens are actually drawn explicitly. So some H's drawn explicitly. So it would be incorrect to just leave a hydrogen out like this. This would communicate a methyl group. So we need to make sure we draw in our H's where they're needed. So one of the remaining questions that we might have about Fischer projections is what the significance of right versus left on these horizontal lines might mean. So if we actually number our carbons within our carbon chain of glucose, we know that the carbonyl carbon is going to take the lowest number we can give it. In this case, it would be 1. And then we would number sequentially, like this. So from that, we can correlate structures between our line angle drawing and our Fischer projection. So if I look at this, carbon 1 and carbon 6, which don't have this horizontal line, those are not stereocenters. But carbons 2, 3, 4, and 5, 2, 3, 4, and 5, those are all carbons that are stereogenic centers. So one of the other things that we can work out from looking at just observing these two representational systems right next to each other for the same structure is that these horizontal lines all correspond to stereogenic centers. Okay, so we've got a few pieces of information about how to interpret Fischer projections here. We know that the left and the right are corresponding to these horizontal lines, and so it does turn out that the position left versus right tells us something about stereochemical configuration. So you could think about this as like whether the center is R or S, whether the OH group is wedged or dashed, but unfortunately, there's a little bit of a problem that we're going to encounter, and that's that in a Fischer projection, right and left on these horizontal lines do not directly correlate with wedges and dashes. This is really important to understand. So left versus right does not equal wedge slash dash. There's no clear correlation. You can convert between line angle drawings and Fischer projections. So there is a system for converting wedges and dashes to left and right, but it's complex and most people don't use it. So it turns out that like many kinds of communication, whether they be graphical or verbal, different kinds of cultures use different kinds of systems. In the same way we have like different languages for different cultures on planet, organic chemists will typically try to use line angle drawings to communicate structure regardless of the kind of molecule that's present, whether it's a sugar or some kind of halogenated benzene or whatever. We're going to use the same drawing system. Biochemists and molecular biologists will typically use Fischer projections to communicate structures of sugars. They typically will not use line angle drawings. And so it turns out that because biochemistry and organic chemistry at some level developed separately, biochemistry coming a little bit later, and even though it's highly related to organic chemistry, had its own epistemological grounding, hasn't been a lot of effort to communicate or to convert back and forth between these drawing forms. So it's actually not something that we're going to cover. But like I said, it is important that you know that you can't like say, oh, well, the rights are wedges and the lefts are dashes. It's not that simple, for instance. Okay? So the last thing that I want us to do then is to think about not ribose, but a different kind of a structure that's actually a stereoisomer of glucose. And that's to actually bring back a sugar we've seen before. We'll look at mannose. So mannose is an aldohexose, and its structure is in line angle form, very similar to glucose. We decided it was actually an epimer of glucose. That was in the previous video. So this is D-mannose. And what I want to do with D-mannose is actually write the Fischer projection for it, but I want to do that by actually comparing D-mannose's stereochemistry to D-glucose. So I can generate this first by knowing, okay, well, I've got a carbonyl. I'm going to place that at the top of my vertical line. And I'm going to have this long vertical line and something at the end, which would be carbon 6, will be my OH group. And I know that I have 6 carbons, so I've drawn 2 so far, and that means I need to have 1, 2, 3, 4 different horizontal lines. But now I need to actually add H's and OH's, and I don't know how to do that. I'm not sure how to correlate wedges and dashes to left and right. But because I already have the Fischer projection for glucose, I can work this out. So if I look at carbon 5, for instance, on glucose and mannose, they're the same. The configuration at carbon 5 is the same. And so, even though I don't know whether left or right always means wedge or dash, I know that for the Fischer projection of mannose, the C5 configuration should be exactly the same as it is in glucose. And then I can keep doing this and working up the chain. So it looks like carbon 4 in glucose and in mannose have the same configuration. So I can use the same configuration in the Fischer projection. Alternatively, if I look at carbon 3, those are also the same. And carbon 2, that's the point of difference. So remember we decided that glucose and mannose are C2 epimers of each other, so they differ in one position out of more than 2, or stereocenters. So I need to communicate like the opposite stereochemical configuration at carbon 2. So in glucose, if my OH group is on the right, then in mannose it would need to be on the left. So one of the things that's nice about Fischer projections is that we can actually very quickly communicate stereochemical differences in a way that's a lot easier to see, for a lot of people anyway, than looking at wedges and dashes. So here what I note is that the configuration at C2 is different between D-glucose and D-mannose, and everything else is the same. So we could look at these two and very quickly make a decision that there's only one point of differentiation at a stereocenter, the things I've circled, and that communicates that D-glucose and D-mannose are C2 epimers, which we already knew, but it confirms it, right? So we're able to use Fischer projections to do this. Okay, so we have a general sense for how to interpret these drawings. We've looked a little bit at how we can correlate differences in stereochemistry because of where OH and H groups line up on the left and right hand sides of these horizontal lines. What's left for us to do is to do a little practice, like making comparisons, for instance, or interpreting structures to answer questions. So in the next section of this video, we'll look at a couple more example molecules. Okay, so we are now looking at D-fructose. So this is a different kind of a sugar. It's a hexose, but now it's a ketohexose. So we've got a C2 ketone. And so one of the things you'll notice in the Fischer projection is that you're going to still orient the carbonyl as close to the top as possible, but now it won't be carbon 1 anymore, it'll be carbon 2. So we'll put our numbers in, carbon 1, carbon 2 we know is associated with the carbonyl here, 3, 4, 5, and 6. If you want and you're curious, you can actually look at this, maybe sketch this Fischer projection of D-fructose in your notebook. And if you rewind the video and actually compare it to the stereochemistry that's shown in the Fischer projection of glucose, you'll see that C3, C4, and C5, OHs are left, right, right, and the same thing is true of glucose because the carbon chain 5, 4, and 3 in D-fructose has the same set of stereochemical configurations as does D-glucose, right? So there's this kind of, again, concept of conserving and comparing stereochemistry between sugar structures. So aside from showing you the Fischer projection of a ketose, the other thing I wanted to do with D-fructose is ask you two questions. So first, what I'd like for you to do is draw a Fischer projection of a stereoisomer of D-fructose, right? So we're changing only stereochemistry. I want you to generate L-fructose. And then I also want you to generate a diastereomer, but not an epimer, of D-fructose. So two different Fischer projections. And I want you to go ahead and try this to make sure that you understand how changes in the drawing of a Fischer projection correlate with different kinds of stereochemical relationships. And then once you've done that, we'll go through these together. So go ahead and pause your video and generate Fischer projections for L-fructose and a diastereomer, not an epimer, of D-fructose. So you've had a chance to draw your Fischer projections. We'll go through these together now. So if I need to generate L-fructose, the first thing I need to consider is, well, what is L-fructose? And I know from the difference in naming that it must be the enantiomer of D-fructose. So that means that I'm going to have all of the same functional groups, all of the same points of attachment, but all of my stereochemical information will be the exact opposite. So I know that this is going to be some kind of it'll be a C2 ketohexose. So I can start by generating the same kind of template for a Fischer projection, where I've got a C2 ketone. That means my C1 will be an alcohol, and my C6 will also have an alcohol that are not stereocenters. I'll still have 1, 2, and 3 stereogenic centers, just like in D-fructose. But if my OH group is on the left, that's C3 of D-fructose, then it needs to be on the right. So I need to change the stereochemical configuration at the C3 position in L-fructose. Again, if C4 is got an OH group on the right, then I need to show the opposite configuration. That means that my OH group would be on the left on C4. Make sure I draw my H specifically. And then again for C5, I'll change the position of OH from right to left to show the opposite configuration at C5. So you can see how fast and valuable Fischer projections can be once you have a good sense for what's being communicated about stereochemistry in these drawings. I look at these structures and I see that everywhere that I have a stereocenter, so everywhere I have those horizontal crossing lines, it looks like my groups have swapped left and right, and that tells me that all of my stereocenters between this structure and this structure are inverted. Okay, so I can use the same kind of a logic to figure out how to draw a Fischer projection for a diastereomer of D-fructose. So we know that diastereomers are also stereoisomers. So what that means is that I'm going to have, again, the same kind of connectivity, same kinds of bonds, same kinds of functional groups. And that means I'm still going to have a C2 ketohexose. So I can start by doing this, drawing my template essentially. It's a little bit like playing hangman. And then I know I'm going to need 1, 2, 3 stereocenters. So let's confirm. I've got 1, 2, 3, 4, 5, 6 carbons. Looks good. So here I've got a few options. Your structure may not be exactly the same as what I'm going to draw, but you should check your structure using the logic that we're talking about here. So we know that a diastereomer is not an enantiomer. Less than all of the stereocenters have changed. So that means I've got two options. I can change 2 of the 3 stereocenters or 1 of the 3. In the instructions, I asked you to avoid making an epimer, which is specifically having 1 of the 3 change. So that means I need to change 2 of the 3 possible stereocenters, and I can choose any 2. There's multiple diastereomers of D-fructose. So I'm going to make a decision and it's arbitrary, that I'm going to change C3 and C4, but I'm going to leave C5 the same. You might have done something different. So if I'm changing C3, then my OH group will be on the right in my diastereomer. My OH group will be on C4 will be on the left. And on C5, I'm going to keep that position constant, and so that means that my OH group on the right of C5 will be also on the right of C5 in the structure I'm generating. So this would be like the C3, C4 diastereomer of D-fructose. So again, your structure might look a little different from this. The idea is that of these 3 horizontal lines, those are your 3 stereocenters, 2 of them should look like they're opposite. You've swapped the configuration. And as long as that's true, you've generated a diastereomer of D-fructose. So this concludes our video where we're discussing the basic mechanics of Fischer projections. In the next videos, we'll look at some reactivity of sugars, and in particular, different kinds of conformations that sugars exist in.